Good morning students. Now coming to remaining DNA structure, double helix model. Students, the simple and famous structure for DNA was proposed by Watson and Crick, scientist Watson and Crick. This is called a double helix model. This is a double helix model for DNA. It was proposed by scientist Watson and Crick. Okay. According to this double helix model, there are two polynucleotide strands. Two strands. There are two polynucleotide strands in DNA molecule. Okay. And these two DNA polynucleotide strands, they are present in a anti-polarity. They show anti-polarity and anti-parallel to each other. What is anti-parallel to each other? One strand is 5' to 3'. And other strand, this is 5' to 3' in reverse direction. So, one strand 5' to 3' in downward position, other one is 5' to 3' in upward position. Both strands are anti-parallel to each other. That is 5' to 3' one strand, and 5' to 3' and another strand in the opposite direction. At the same time, these two strands, they contain nitrogen base pair. Okay, one of the hallmarks of this double helix model of DNA, one of the most important hallmarks, that is base pairing between nitrogen bases. Base pairing. Okay. Here, the nitrogen bases they show complementarity in between them. Complementarity means always adenine. It is complementary with thymine by two hydrogen bonds. Actually, this is a purine. Adenine is purine, thymine is pyrimidine. One purine adenine and one pyrimidine thymine, they are linked by two hydrogen bonds. They are matching letters. They are complementary to each other, and vice versa. That is, thymine is complementary with adenine by two hydrogen bonds. Okay, thymine is complementary with adenine by two hydrogen bonds. Similarly, another purine, this is guanine. Always this guanine purine, it is complementary with cytosine by three hydrogen bonds. So, the hydrogen bonds ratio present between A and T and G and C 2:3. This is purine, this is pyrimidine, and vice versa. This nature of nitrogen base is present in DNA. This is called a complementary relation. Complementary relation. This is a complementary relation. So the nitrogen present in DNA, they show complementarity between them. What's complementarity? Matching. Adenine is linked with thymine by two hydrogen bonds, and vice versa. Thymine, guanine linked with cytosine by three hydrogen bonds, and vice versa. This nature, this relation of nitrogen bases in DNA, that is called complementary relation. Okay, complementary relation. Similarly, always the purines present in DNA, they are linked with pyrimidines. Purines linked with pyrimidines. The purines of one strand linked with the pyrimidines of other strand. Purines and pyrimidines, they are complementary in nature. Purines and pyrimidines are linked by hydrogen bonds and are present in complementary relation. So that purines and pyrimidines, they exist 1:1 ratio according to Chargaff rule in DNA molecule. Anyhow, nitrogen bases are 4 types. There are 2 pyrimidines and 2 purines. Purines and pyrimidines are exist 1:1 ratio and they are linked one to each other. In this way, for example, this is a polynucleotide strand, this strand and second strand. Number of nitrogen base pairs, they are projected from this backbone but facing towards the lower side. They are nitrogen bases, pairs, nitrogen base pairs. Many nitrogen base pairs are established between the 2 polynucleotide strands of one DNA molecule. Nitrogen bases are projected from the backbone but facing towards the lower side. In this way, number of nitrogen base pairs are established transversely between the 2 polynucleotide strands, just like the steps in a ladder. The steps in a ladder, it gives an appearance of a ladder. In this way, the 2 strands, they are spirally coiled. The 2 strands, they are spirally coiled in right-handed fashion. In right-handed fashion. Okay? The 2 strands present in DNA molecule, they are spirally coiled in right-handed fashion, resulting like this. This is one of the strand. Okay, this is 5 strand to 3 strand in downward direction, and this is the next strand. This is 5 strand to 3 strand region in upward direction, and many nitrogen base pairs. So 2 strands in DNA molecule, they are spirally coiled to each other. Spirally coiled and held to each other by number of nitrogen base pairs. Hydrogen bonds present between nitrogen base pairs. So, spirally coiled, and each and every coil, every turn, this is called a coil or turn or helix. Due to spiral arrangement of the 2 strands in DNA molecule, it leads to the formation of several coils, several turns, several helix. Okay, in this way, every helix coil, it is length of coil is 34 angstroms. Length of coil is 34 angstroms. Now coming to the most important points in objective purpose, measurements of DNA. Measurements of DNA. Okay. 1. Length of coil. Very important. Length of coil. Okay. Length of coil. This is 34 angstroms length. 34 angstroms length means what about in nanometers? This is 3.4 nanometer. 1 nanometer is equal to 1 billionth part of a meter. That is 10 power minus 9 meters. 10 power minus 9 meters. 10 power minus 9 meter. 1 nanometer is equal to 1 billionth part of the meter, that is 10 power minus 9 meters. Length of coil is this is 34 angstroms. Okay, very important students. Now coming to another point. Actually, the length of DNA molecule, this is uncertain. First coming to DNA length. Uncertain, very important. Length of DNA. Length of DNA. This is uncertain. Uncertain. Uncertain means there is no the standard length for DNA molecule, and it is mainly based on the number of base pairs, number of nucleotides. Greater the number of nucleotides in any DNA molecule, automatically length is also greater. Okay, length of DNA is uncertain, and diameter of DNA. So DNA length is uncertain, but diameter is certain, means constant. This is 20 angstroms, that is 2 nanometers. 20 angstroms means 2 nanometers. Length is uncertain, is based on the number of nucleotides, but diameter of DNA is standard. This is 20 angstroms, means 2 nanometers. Now coming to information for one coil. Length of coil. Length of coil. Okay. Length of coil. This is 34 angstroms. 34 angstroms in nanometers. 3.4 nanometers. 1 nanometer is equal to 1 billionth part of the meter, that is 10 power minus 9 meters. And length of coil is 34 angstroms. And number of base pairs, very important. Number of base pairs per coil. How many base pairs are present in one coil? 10 base pairs are present. 10 base pairs. Okay? 10 base pairs. And what about the number of nucleotides? Number of nucleotides. Base pairs 10. What about the number of nucleotides? 10 into 2. That is 20 nucleotides. 20 nucleotides. 10 into 2. There are 10 base pairs. Okay, each pair is represented by 2 nucleotides, so 10 into 2 is equal to 20 nucleotides. And length between the successive pair, length between the pair, very important, length between the pair. Total length of coil is 34 angstroms. Here 10 base pairs are there. And what is the length between successive base pairs? 34 divided by 10. That is equal to 3.4 angstroms. This is 3.4 angstroms. That is in nanometers 0.34 nanometers. That is the length between two successive base pairs. Now coming to another point. Total purines or the total angle of coil. Total angle of coil 360 degrees. 360 degrees. But what is the angle between the successive base pair? Angle between base pair. Angle between base pair. There are total 10 base pairs. Total angle is 360 degrees. 360 divided by 10, that is equal to 36 degrees. There are total nucleotides 20 nucleotides. And among these 20 nucleotides, what is the number of purines? What is the number of purines? Always 50% purines and 50% pyrimidines. Purines and pyrimidines in DNA, they show 1:1 ratio. Total 20 nucleotides are there. 10 purines are 10. And what about the number of pyrimidines? Number of pyrimidines also 10. Number of pyrimidines also 10. So purines and pyrimids, they exist 1:1 ratio. 1:1 ratio. Now coming to another point. What about the maximum number of H bonds? For example, there are total 10 base pairs. What is the maximum number of hydrogen bonds present in one coil? Maximum number, that is 30. Why maximum number of hydrogen bonds is 30? For example, there are 10 base pairs. If these 10 base pairs are in case of A and T pairs, okay? If the 10 base pairs are in case of G and C base pairs, 10 G's and C base pairs, each pair is represented with 3 hydrogen bonds. 10 into 3 is equal to 30. It is in case of 10 base pairs in case of G and C. When 10 base pairs, if they are in G and C in condition, 30 maximum hydrogen bonds are there. But what about the minimum number of maximum or minimum number of H bonds? Minimum number of H bonds, that is 20. If it is in case of A double bond T or T double bond A, that is, this gives when the 10 base pairs are A and T. If in case of this situation, it gives the minimum number of hydrogen bonds, that is 10 into 2, that is equal to 20. And what about the CN rings? Number of CN rings, total number of CN rings. What is CN ring? Each purine is represented by 2 CN rings in their molecular structure. Each purine with 2 CN rings. Similarly, each pyrimidine, it consists of 1 CN ring. So, total number of purines 10. 10 into 2, 20. Total number of pyrimidines 10. 10 into 1, 10. 20 plus 10, 30. Maximum, number of CN rings, 30 CN rings are there. Among these 30 CN rings, how many CN rings are present in purines? 10 into 2, 20. How many are present in pyrimidines? 10 into 1, 10. What is the ratio of the CN rings present in purines and pyrimidines? 20:10. That is equal to total 30 CN rings are there. 30 CN rings. Now coming to another point, very important point. The number of glycosidic bonds. Okay, already know this point in previous class. Glycosidic bonds is equal to N. N means nucleotides. What is the total number of nucleotides here? 20. Always glycosidic bonds are equal to N. N means nucleotides. 20. Okay. And what about the number of ester bonds? What is the formula for ester bonds calculation? Here, this is equal to N. And what about the ester bonds? Ester bonds means 2n minus 2. 2n minus 2. What is 2n? 20 nucleotides are there. 20 into 2, 40. Minus 2, 38. So, 38 ester bonds are there. Because there are total 20 nucleotides. 20 into 2, 40. Minus 2, 38. And what about the phosphodiester bonds? Phosphodiester bonds, very important. Phosphodiester bonds 2 means n minus 2. N is equal to 20 minus 2 is equal to 18. Okay, n is equal to 20. So total 60 statements are there in measurements of DNA molecule. They are most important measurements to solve the problems regarding DNA molecule. These measurements are necessary. One, length of DNA is uncertain. Diameter of DNA is 20 angstroms, that is 2 nanometers. Length of each coil is 34 angstroms, that is 3.4 nanometers. And number of base pairs 10, nucleotides 20. Length between pair 3.4 angstroms, 0.34 nanometers. Total angle 360. Between base pair 36. Total purines 10. Total pyrimidines 10. Total hydrogen bonds, maximum hydrogen bonds 30 and minimum 20. Number of CN rings 30 and number of glycosidic bonds is equal to N, means 20. Number of ester bonds 2N minus 2, that is equal to 40 minus 2, that is equal to 38. Number of diester bonds is equal to N minus 2, N is equal to 20, minus 2 means 18. They are the measurements, the most important measurements for the calculation of any problem regarding the DNA molecule. Okay, now coming to another point. After immediate to the proposition of this double-stranded, double helix model for DNA, Watson Crick, scientist, especially scientist Crick, proposed the central dogma of molecular biology. Central dogma of molecular biology. Central dogma of molecular biology proposed by scientist Crick. And immediate to the proposition of double helix model for DNA, Watson proposed a central dogma of molecular biology. And what is the central dogma of molecular biology? Central dogma of molecular biology. It explains the transformation of genes from DNA to proteins. The transmission of genetic code from DNA to proteins. DNA to proteins. The transfer of genetic material from DNA to proteins is called central dogma of molecular biology. It explains the genetic flow in protein synthesis. It explains the genetic flow from DNA to RNA. It explains the genetic flow from DNA to RNA during protein synthesis. So, according to this central dogma of molecular biology, this is DNA. Okay. This DNA, it is also replicates to form daughter DNA molecules. This is called replication. This is replication. What is replication? DNA to DNA is called replication. That is, formation of daughter DNA molecules from parental DNA is called replication. Multiplication of one parental DNA into two daughter DNA molecules is called replication. Now, during protein synthesis, the genetic information present in DNA first it is copied into mRNA, messenger RNA. Okay, this process is called replicate. This is called transcription. Transcription. It takes place in a nucleus. What is transcription and where it takes place? Formation of mRNA from DNA, blueprint. The transfer of genetic material from DNA blueprint to mRNA. This is called transcription. It takes place in nucleus. First step, this is the first step of protein synthesis. What happened in first step of protein synthesis? First, the genetic information present in DNA blueprint is copied onto mRNA. This is transcription. In second step, the genetic information present in mRNA, it is decodes into proteins. This process means formation of proteins from mRNA. This is called translation. This is translation. It takes place in a cytosol. This is called central dogma of molecular biology. There are two steps in protein synthesis. In first step, genetic material is copied onto mRNA from DNA blueprint. This is called transcription and it takes place nucleus. In second step, genetic information is decoded into proteins. That is, formation of proteins from mRNA is called translation. It takes place in a cytosol. Students, in some members, for example, retroviruses like HIV is one of the retrovirus. HIV. What is the genetic material of HIV? This is RNA. Okay. Formation of mRNA from DNA is called transcription, and formation of DNA from mRNA reverse direction. This is called reverse. Formation of RNA, formation of DNA from RNA, reverse. This is called reverse transcription. Reverse transcription. Reverse transcription is present in some retroviruses like HIV. So, genetic flow from DNA to RNA is transcription. But reverse direction, that is genetic flow from RNA to DNA, this is called reverse transcription. Generally, it is present in HIV. So, central dogma of molecular biology, it explains the genetic flow from DNA to RNA. This is called central dogma of molecular biology, proposed by scientist Crick.